Now in this chapter we will discuss about resolution of vectors. The process of splitting a vector into its components is known as resolution of vector. So if we are having a vector in a plane, we can resolve the vector into its components. Let us see how we will do it. Let us see the resolution of vector into its component using a rectangular coordinate system. Let us consider a vector A that lies in a plane xy, and as you can see in the diagram, the vector A is in the xy plane. Now we can resolve this vector into its components, that is the component of vector A along the x-axis and the component of vector A along the y-axis. So a vector placed in xy plane can have its components along both x-axis and y-axis. And we have already discussed here the unit vector along x-axis is I cap and unit vector along y-axis is j cap. So we will be having the component of vector A along I cap direction and component of vector A along j cap direction. Let us consider our vector is making an angle theta with the horizontal axis, that is the x-axis. Now when the vector A is making an angle theta with x-axis and it is placed in xy plane, we can resolve this vector into its component. For that, we draw two perpendiculars from the head of the vector A to both x-axis and y-axis. The perpendicular from the head of vector A meets at x-axis at the point P, and the perpendicular drawn from head of the vector A meets on the y-axis at the point Q. So OQ here is the y component of our vector A and OP is the x component of our vector A. Now considering the triangle OPQ dash, which includes the vector as its hypotenuse, we can write from here sin theta is equal to opposite by hypotenuse, that is q dash p divided by vector A, and cos theta is equal to OP by vector A. So we obtain the expression for cos theta as OP by OQ dash, which is the vector A itself, and sin theta is PQ dash by OQ dash, and PQ dash is equivalent to the OQ distance, which is the y component represented as AY, and OP is the x component represented as AX, and we already said OQ dash is the vector. So we take the value of OQ dash as the magnitude of vector A. So till now we have considered a vector A which is placed in an xy plane, and we have drawn two perpendiculars from the head of the vector to x-axis and y-axis, and OP represents the x component whereas OQ represents the y component. And to obtain the values of OP and OQ, we consider the triangle OPQ dash, which has the vector as its hypotenuse. Then we saw that cos theta is OP by OQ dash and sin theta is PQ dash by OQ dash, and OP is the x component, PQ dash is the y component. Thus we can write cos theta is equal to AX by A, where AX is the x component and A is the magnitude of vector A, and sin theta is equal to AY by A, where AY is the y component and A is the magnitude of vector A. And from these two we can write AX, which is the x component of our vector, as A cos theta, and AY is equal to A sin theta. The y component AY is obtained as A sin theta. So thus we resolved a vector A which is making an angle theta with the x-axis into its x component AX is equal to A cos theta and y component AY is equal to A sin theta. So now we can represent in the component form our vector A as AX I cap plus AY j cap, and which can be written as A cos theta I cap plus A sin theta j cap. So this is the component form of our vector. after resolution. So any vector which is making an angle theta with the horizontal axis, that is the x axis, can be resolved into its components, that is x component and y component, and we obtain the x component as magnitude of vector into cos theta and y component as magnitude of vector into sin theta. And from this we can also obtain the relation that if we are having a vector in its component form, then we can obtain the magnitude of the vector as root of ax square plus ay square. And here if we substitute the values of ax and ay, we can see that we obtain a itself. So the magnitude of a vector can be obtained by the expression root of ax square plus ay square. And also to obtain the angle made by the vector, that is theta, we divide both the expressions of ax and ay, and we obtain the relation as tan theta is equal to ay by ax. So by taking the ratio of the y component to the x component, we obtain the tan value of our angle, and from which we can write theta is equal to tan inverse of ay by ax. So by analyzing the resolution of vector, we have seen that a vector can be resolved into its x component and y component, and also if we are having a vector in its component form, we can find the magnitude of vector given by magnitude of vector a is equal to root of ax square plus ay square, and also the angle made by our vector can be obtained as theta is equal to tan inverse of ay by ax. So in general, we can represent a vector in its component form if it is in a three-dimensional space as A is equal to vector A is equal to ax I cap plus ay j cap plus az k cap. And also here the magnitude of vector A can be written as A is equal to root of ax square plus ay square plus az square. And the position vector in a three-dimensional space can be expressed in general as r, the position vector r is equal to x I cap plus y j cap plus z k cap. Now we will see how can we add two vectors and subtract two vectors when they are given in their component forms. Suppose we are having two vectors, a is equal to vector A is equal to ax I cap plus ay j cap plus az k cap, and vector B is equal to bx I cap plus by j cap plus bz k cap. To add these two vectors, we write the sum as r is equal to vector A plus vector B, which is equal to ax plus bx I cap plus ay plus by j cap plus az plus bz k cap. So what we are doing here is we are adding the corresponding components, that is x components of both the vectors are added, and that will be the magnitude of resultant vector in its I cap direction. And by adding the y components of both the vectors, we obtain the component of the resultant in j cap direction, and by adding the components z components of both the vectors, we obtain the resultant component in the k cap direction. So if we are having two vectors in its component form, we get the resultant by adding the components, corresponding components of both the vectors. Now similarly, to get the difference of two vectors a and b, what we do is we subtract the corresponding component vectors, that is, let here also we represent the difference of two vectors by vector r, and vector r is equal to vector a minus vector b, which is equal to ax minus bx I cap plus ay minus by j cap plus az minus bz k cap. In order to add or to subtract two vectors given in component forms, we add the corresponding components or we subtract the corresponding components, and thus we obtain the resultant. Now we are going to see the vector forms of position, displacement, velocity and acceleration. So as we told, position can be in general represented as a vector given by vector r is equal to x I cap plus y j cap. Suppose we are having a particle P which is at a position represented by the position vector r given by xi cap plus yj cap. What this means is the particle P is in an xy plane such that its distance along x axis is x and its distance along y axis is y. So, we represent altogether the position as xi cap plus yj cap. So, here a particle P in an xy plane is represented by its position vector r is equal to xi cap plus yj cap. Now, let us consider the particle P changes its position from r to r dash, that is the vector r now has become r dash, and r dash is given by x dash I cap plus y dash j cap. So, the position of our particle now has become r dash, that is x dash distance is covered along x axis and y dash distance is covered along y axis. Therefore, r dash is represented as x dash I cap plus y dash j cap. So, this is how we represent the position vector, and now to get the displacement, we know that displacement is final position minus initial position, and to obtain the displacement vector we find the difference between the final position vector and the initial position vector. Final position vector is x dash I cap plus y dash j cap and initial position vector is x I cap plus y j cap. So, by finding the difference in the position vectors r dash and r, we get x dash minus x I cap plus y dash minus y j cap as the displacement vector delta r. So, the vector delta r is equal to delta x I cap plus delta y j cap, where delta x is x dash minus x and delta y is y dash minus y. So, if we are having the vectors r dash and r in a plane, by joining the vectors, that is from the head of r to head of r dash, we obtain the delta r vector, that is the displacement vector. This is how the displacement vector of an object is obtained in xy plane. Now, coming to the velocity vector, v is the ratio of displacement and time interval. So, vector v can be written as displacement vector divided by time interval, that is delta r divided by delta t. And we know that the displacement vector delta r is delta x I cap plus delta y j cap. So, dividing this vector by delta t, we obtain the velocity vector. So, velocity vector is written as delta x by delta t I cap plus delta y by delta t j cap, and we can write it as vector v is equal to vx I cap plus vy j cap, where vx is delta x by delta t and vy is delta y by delta t. So, in the component form, we obtain the vector velocity vector v as vx I cap plus vy j cap. Thus, the vector form of the average velocity v can be written as delta r divided by delta t. Now, to get the instantaneous velocity in its vector form, we know that we have to put the limit for delta t tending to 0, that is time interval tending to 0. That is, by putting time interval tending to 0, we obtain instantaneous velocity from the average velocity. Thus, the instantaneous velocity vector v is equal to limit delta t tending to 0 delta x by delta t I cap plus limit delta t tending to 0 delta y by delta t j cap. And we can write this as velocity vector v is equal to dx by dt I cap plus dy by dt j cap. So, by taking the differentiation of the individual components, we obtain the instantaneous velocity vector. Thus, the instantaneous velocity vector is obtained as vector v is equal to dr by dt, that is, by taking the differentiation of the position vector, we obtain the instantaneous velocity. and the components we can write here as Vx, the x component of the instantaneous velocity vector, as dx by dt, and the y component of the instantaneous velocity vector as dy by dt. Now, to get the acceleration in its component form, we divide the velocity with time interval. So, average velocity vector A is given by delta v by delta t, where delta v is the average velocity vector, and we know that v is Vx I cap plus Vy j cap. Therefore, delta v by delta t can be written as delta Vx by delta t I cap plus delta Vy by delta t j cap. Thus, the x component of acceleration vector Ax is delta Vx by delta t, and y component of acceleration vector Ay is delta Vy by delta t. Now, to get the instantaneous acceleration vector, we put the limit of delta t as 0, and here also we obtain the differentiation form, that is instantaneous acceleration vector A is equal to dvx by dt I cap plus dvy by dt j cap. And here also the x component of instantaneous acceleration vector A is Ax equal to dvx by dt, and y component is Ay is equal to dvy by dt. So, this is how we represent the acceleration in the vector form or the component form. Now, we are going to obtain the component form or the vector form of the equations of motion. We know that the equation of motion v is equal to u plus at, where v is the final velocity, u is the initial velocity, a is the acceleration, and t is the time. Now, to write the component form of this equation of motion, we first consider the x component. So, to get the x component of this equation of motion, we take the x component of all the quantities used here, that is Vx is equal to ux plus Ax into t, and to get the y component we express it as Vy is equal to uy plus Ay into t. Similarly, for the equation of motion s is equal to ut plus half at square, here also we can obtain the component form. We know that s here is the displacement, u is the initial velocity, t is the time, and a is the acceleration. So, to obtain the x component, the displacement can be represented as x minus x naught, which is equal to ux t plus half Ax t square, and y component is given by y minus y naught is equal to uy t plus half Ay t square.